So one of the nice things about doing these problems on YouTube is that I can solve them ahead of time, figure out what's right, and then record only the good stuff. So for example, in this problem, it's either rolling without slipping or slipping while it's rolling, and you really don't know ahead of time. And so you have to guess one, solve the problem, and check the condition at the end, like it's a friction force less than mu times n. And then if it's not, you have to redo it. So in this case, this wheel or disc ring is sliding while it's rolling. But I'm going to show you the wrong answer first so you can see how it goes. Like you guess the wrong thing, you check it, you see, oh no, that's wrong, and then you have to restart it. So I'm going to do that. And it occurs to me that on a test, I'm not going to say, oh, this is the energy problem, and oh, this is the F equals ma problem. And so when you read these things, and you see something like the time t for the hoop to move a distance of 10 feet. Okay, so if it's the energy problem, energy only involves distances. Okay, the work is force times distance. The potential energy due to gravity, mg times the height. Potential energy due to the spring, 1/2 kx squared. And it involves velocities, 1/2 mv squared, 1/2 I omega squared. So as this problem is asking you to solve for a time t, it's obviously not an energy problem. Now, we have not covered momentum yet for rigid bodies, so it is possible that this problem might be able to be solved with momentum principles, but for this test, we're not including that. So this is definitely an F equals ma problem. And so the first step in any F equals ma problem is to draw the free body diagram. And so this free body diagram is exactly like the one with the disc. You've got the weight going down vertically, normal force perpendicular to that 20-degree slope. Last problem was 30 degrees. And again, because I'm assuming that it is not slipping, that friction force is not mu times n. It's an unknown friction force which we'll have to solve for. Okay, on the right-hand side, you always have ma applied at the center of gravity, which is not physically on the ring. It's actually interesting. It's in the middle of that ring, and I alpha is applied anywhere, but we put it there, right there. Okay, so for no slip, you don't get to know what the friction force is, but you do know, we've talked about this in the previous problem, if it's not slipping, the bottom of the ring has zero acceleration because it's touching the ground, and the ground has no acceleration. That means that the acceleration is alpha times r, literally r, which is the radius of the ring. That's the distance from the bottom to the center. And the radius is 6 inches, or I'm doing everything in feet, so 1/2 foot times alpha. The friction force needs to be less than mu times n. We'll check it. I can see the future because I already solved it. That is not going to be true. Okay, so another interesting thing about this problem is that the mass is not given, but that's not a mistake. You're given this hint, the mass will cancel out of all the equations. So if it bothered you, it messed you up, you could have just said, hey, mass is 1 and solved it. I'm going to just leave mass equals m and solve it, and you'll see that it cancels out. Okay, so again, I'm going to take the y component first because I saw last time that that's going to just give that you can solve for n. So if you look at the left-hand side, you have mg, which is a weight, and it has a component going in the y direction of cosine 20 degrees. So n is going up, the weight cosine 20 degrees is going down, so negative. And on the right-hand side, there's no y acceleration because, again, the ring is not hopping up off of the ground, so that's 0. And so you immediately solve that for n equals the weight times cosine 20 degrees. We don't know the mass, so it'll be m times g times cosine 20 degrees. Okay, so now I definitely know this ring is rolling downhill. There's no ropes attached, so I'm not going to get this wrong. So I'm taking x positive downhill, and so the weight has a component downhill of mg sine 20 degrees. The friction force unknown is pointing up. That's all there is on it, and it's equal to ma going downhill, and we just did the kinematics. A is actually 1/2 foot radius times alpha, so I just put in A as 1/2 alpha, so 1/2 m times 1/2 alpha, or 1/2 m alpha. Okay, and then again, I'm choosing to take moments about the bottom so that the N and the friction force don't come into play. So taking moments about the bottom, the X component of the weight is mg sine 20 degrees. The moment arm is the radius, which is 1/2 foot. Okay, on the right-hand side, you're taking moments about the bottom, same thing, ma times its moment arm is the radius of 1/2 foot, and you just add in I alpha. Okay, and again, A is 1/2 alpha. Okay, 1/2 foot radius times alpha, that's A. And so that comes out to M times 1/4 alpha plus 1/4 M alpha. 2/4 is 1/2, so 0.5 M alpha. So if you cancel the M's on both sides, so mg sine 20 degrees, 0.5 M alpha, you get 1/2 g sine 20 degrees is 0.5 alpha, and the halves cancel, that 0.5 and 1/2, so you end up with alpha equals sine 20 degrees times g. Okay, so I'm going to take that alpha, put it into equation 2 and solve, so you get mg sine 20 degrees minus f equals 1/2 m alpha, but alpha is sine 20 degrees g. So there we go. That is alpha. Okay, and you just simplify that out. You've got put the f on one side, bring the 1/2 mg on the other side, and you end up with this. And solve it for the friction force. So before we go any further, and plus I already knew that it's slipping, let's check if it's slipping. So is this friction force less than mu static times the normal force? So no, I am not doing the solution al fresco outdoors. I have my clock in my office is an alarm clock that chimes on the hours with different bird chimes. So if it happens again during this little video, that means I've spent another hour on this. Okay, so anyway, let's continue. So the friction force was 1/2 sine 20 degrees mg. Okay, this was mu static was 0.15, and then we got the normal force was cosine 20 degrees times mg, and as promised, m cancels out. Or you could have just put m equals 1 and solved the problem. Okay, so 1/2 sine 20 degrees is 1.710, and 0.15 cosine 20 degrees is 0.141. It is not less, so no, it is not rolling without slipping. It is slipping. So if you get to this point, it means you have to redo and guess that it is slipping and continue on. Okay, so this brings the question, and so what that means is that the friction force will be mu kinematic 0.12 times n, but what it also means is we can no longer say that A equals R alpha, because that bottom point of the disk is not the pinpoint. It is definitely moving and accelerating at the bottom of the disk. So again, what that means is we're going to redo the problem with these new assumptions right here. Okay, so that begs the question, if you guess wrong, you're going to end up doing the problem twice. And if you guess correctly, you only do the problem once. And so you're kind of wondering, is there any way to know beforehand if it'll slip? And not really. However, we can learn some things about this. So if it's not slipping, okay, we want the right-hand side. So let me write this thing out again. we have 1/2 sine 20 degrees is less than 0.15 cosine 20 degrees, okay? Where that was mu. So when the right-hand side is greater than the left-hand side, it will not slip. And so I'm thinking, what makes the right-hand side big and the left-hand side small? So if the coefficient of friction is high, the right-hand side is big. Also, what angle makes the cosine big and the sine small? Well, small angles, for example, 0. Cosine of 0 is 1, sine of 0 is 0. If it's flat, it's not going to slip. So theta is low. Now, we didn't have to do math to figure this out. Basically, what this says, if it's not very steep and you have like a really high coefficient of friction and it's real grippy, that's not going to slide. It'll roll. That makes sense. The opposite really makes sense to me. If it's steep and it's slippery like ice, if you've ever been on an icy roof that's steep, you know that is bad news. You're going to slide down that roof. So it makes sense. Steep and slippery, you'll slide down the hill. Flat and sticky, you will not slide down the hill. It's that simple. Okay, so again, let's continue the problem knowing that we guessed wrong. It was hard to tell if it was going to slip or not. So in this case, it was a 50-50 chance. We guessed wrong, and we're going to go again. So it's definitely slipping. We just proved that. And so what's changed now is the friction force. It's 0.12 N. And the other thing is we can no longer say that A is R times alpha. That's the new unknown. So basically we're swapping unknowns. This used to be unknown, the friction force, but now it's known. The A used to be known as R alpha, but now this is unknown. Okay, so let's keep going. Okay, so this is a free body diagram. I've basically just copied it from above. The only difference is I replaced that unknown friction force with 0.12 N, where 0.12 is the kinematic coefficient of friction. Okay, and so we're going to do the same thing now. We'll do the y direction. We get actually the same equation. N going up minus mg cos 20 degrees coming down equals 0. So N is still mg times cosine 20 degrees. Now we're going to do x going downhill. It's definitely rolling downhill. So mg sine 20 degrees, that's the same. So this is what's different. It used to be minus the friction force, but we know now that the friction force is mu times n, 0.12 times n, because it's sliding, and it's ma going down the hill. Now, A is not R times alpha anymore because it's slipping. Okay, so all we're going to do is we're going to put in n equals mg cosine 20 degrees right into there for n. So mg sine 20 degrees minus 0.12 mg cosine 20 degrees equals ma. We'll be able to solve for a. Nicely, as promised before, the m's cancel out, and you solve for a. A is just sine 20 degrees minus 0.12 cos 20 degrees, and that comes out positive 0.2293. Now, if it was slipping, that would have come out negative, but we don't have to. If it was not slipping, that would have come out negative, but we don't have to check that. We already did that. So 0.2293 times g is 32.2 feet per second, is 7.384 feet per second squared. And I wanted to know how long it took to go 10 feet. And so you got to go all the way back to chapter 2, the kinematics for just a particle moving, because remember, the center of the ring moves like a particle. Is x equals x0, the initial displacement, which was 0, the initial velocity, it was released from rest, times t, 1/2 at squared. We went through all that trouble to get that a was 7.384 feet per second squared. And you solve, and you get t is 1.7 seconds. Okay, it also asks for alpha of the ring. So this time, instead of taking moments about the bottom, I'm going to take moments about the middle because I want to get rid of MA and just to show you something different. Okay, so I took moments about the middle. The mg goes to the middle, the n goes right through the middle, and so I'm taking moments about right here. So you just have the friction force, 0.12 n, okay, and it has a moment arm of 1/2 foot equals I alpha, and we figured out earlier m was 0.25 m. I was 0.25 m. And we know that n was mg cosine 20 degrees. And again, the m's cancel out. That's nice. And you can solve for alpha. And alpha is 0.2255 g, which comes out to 7.26 radians per second squared.